Welcome to the live session where we'll go over chapter 2 of the Hugging Face course. I'm joined by Lewis, who is on the chat and who is going to answer all your questions quicker than I will. And don't hesitate to ask all your questions because I'm going to read them aloud and answer them on the live stream. That's like the main advantage of following this live stream instead of just watching the course by yourself. Inside this chapter 2, we'll look at the pipeline object that we used at length during chapter 1 on all NLP tasks. And we'll see exactly how it works. We'll see how it loads the model, how it preprocesses the inputs with a tokenizer, and then how it post-processes those outputs to get the predictions and probabilities that we got during chapter 1. So we'll watch a few videos, I'll answer all the questions that you have, and we'll do more live coding than in chapter 1 because chapter 1 was just a general introduction and there is a lot of more code in chapter 2. So as an introduction, as you may know, Hugging Face is mainly known for its transformers library, which is a library containing a lot of transformers models, and it provides an easy API to download pre-trained model and to use the different architectures. I think there are more than 60 architectures now available in the library. And it all exposes a unified API, but inside and provides you with either a Torch module or a TensorFlow Keras model that you can use by yourself or that you can train with the API that the library also provides. And the goal is so ease of use, flexibility, and simplicity. And the library doesn't contain any abstraction at all. It's not a library composed of building blocks. Every model, every one of the 60 architectures I was talking about, is completely defined in its own modeling files. So you can have a quick look, for instance, at the modeling BERT file, which contains all the code of the BERT model inside the library. As if you look at the import, you see like there are just Torch imports and then some internal classes that this uses, but which are shared between all models, which are mainly the output types that we use. We'll see exactly what those outputs are a little bit later when we code. But there is no other imports. There is not like an attention block that we reuse across model. The attention block for the BERT model is defined inside this modeling file. So you have the BERT embeddings, you have the BERT self-attention, etc., etc. And the idea is that if you want to play around with the model and change a line of code inside the model, you won't have to learn 50 different files. It's not subclassing something, but subclassing something, but subclassing something. Everything, I'm just realizing I'm hiding a bit. Oh, it's okay, I guess. I'm just going to scroll faster. You have everything in that modeling BERT file, and you can play around and modify everything you want if you want to experiment with it. And that's really one of the strengths of the Transformers library, one of the features that our users have said they like a lot, which is why I wanted to show it to you briefly. And so yeah, we'll see how the pipeline API loads that BERT model. It was actually a distilled BERT model that we used in chapter 1. And the corresponding tokenizer, and how to do everything that this pipeline function was doing by hand, so that you can tweak any of those steps if you need to on your own tasks. So let's begin with the first section and the first video. We're going to watch this introductory video that's going to present what's happening behind the pipeline. I'm just not going to stream them from YouTube because that's making the live stream lag a lot. I have all the videos locally. So if you give me just 1 minute, I'm going to extract it and play it from my computer. What happens inside the pipeline function? In this video, we'll look at what actually happens when we use the pipeline function of the Transformers library. More specifically, we'll look at the sentiment analysis pipeline and how it went from the two following sentences to the positive and negative labels with their respective scores. As we've seen in the pipeline presentation, there are 3 stages in the pipeline. First, we convert the raw text to numbers the model can make sense of using a tokenizer. Then, Those numbers go through the model, which outputs logits. Finally, the post-processing steps transform those logits into labels and scores. Let's look in details at those 3 steps and how to replicate them using the transformers library, beginning with the first stage, tokenization. The tokenization process has several steps. First, the text is split into small chunks called tokens. They can be words, part of words, or punctuation symbols. Then, the tokenizer will add some special tokens if the model expects them. Here, the model used expects a CLS token at the beginning and a SEP token at the end of the sentence to classify. Lastly, the tokenizer matches each token to its unique ID in the vocabulary of the pre-trained model. To load such a tokenizer, the Transformers library provides the AutoTokenizer API. The most important method of this class is FromPretrained, which will download and cache the configuration and the vocabulary associated to a given checkpoint. Here, the checkpoint used by default for the sentiment analysis pipeline is Distilbert based on case fine-tuned SSS2 English, which is a bit of a mouthful. We instantiate a tokenizer associated with that checkpoint, then feed it to the 2 sentences. Since the 2 sentences are not of the same size, we'll need to pad the shortest one to be able to build an array. This is done by the tokenizer with the option padding equal true. With truncation equal true, we ensure that any sentence longer than the maximum the model can handle is truncated. Lastly, the return tensors option tells the tokenizer to return the PyTorch tensor. Looking at the result, we see we have a dictionary with 2 keys. Input IDs contains the IDs of both sentences, with 0 where the padding is applied. The second key, attention mask, indicates where padding has been applied, so the model does not pay attention to it. This is all what is inside the tokenization step. Now let's have a look at the second step, the model. As for the tokenizer, there is an AutoModel API with a FromPretrained method. It will download and cache the configuration of the model, as well as the pretrained weights. However, the AutoModel API will only instantiate the body of the model, that is, the part of the model that is left once the pretraining head is removed. It will output a high-dimensional tensor that is a representation of the sentences passed, but which is not directly useful for our classification problem. Here, the tensor has 2 sentences, each of 16 tokens, and the last dimension is the hidden size of our model, 768. To get an output link to our classification problem, we need to use the AutoModel for sequence classification class. It works exactly as the AutoModel class, except that it will build a model with a classification head. There is one autoclass for each common NLP task in the Transformers library. Here, after giving our model the 2 sentences, we get a tensor of size 2 by 2, one result for each sentence and for each possible label. Those outputs are not probabilities yet. We can see they don't sum to 1. This is because each model of the Transformers library returns logits. To make sense of those logits, we need to dig into the third and last step of the pipeline, post-processing. To convert logits into probabilities, we need to apply a softmax layers to them. As we can see, this transforms them into a positive number that sum up to 1. The last step is to know which of those correspond to the positive or the negative label. This is given by the ID2label field of the model config. The first probabilities, index 0, correspond to the negative label, and the seconds, index 1, correspond to the positive label. This is how our classifier built with the pipeline function picked those labels and computed those scores. Now that you know how each step works, you can easily tweak them to your needs. And I am back. I think there's something wrong with the webcam. Let me just double check. Okay, so somehow my head disappeared. I don't know why exactly. If you can see it, feel free to say it in the chat. In the meantime, there is a question. What does the triple dot signify in from ... activations import act to function in the py files shown? Very good question. So this is standard Python. If you're building a package in Python and you're trying to import things, you have several levels. So it's because of the structure of the transformer repo. Let me try to pull it back. I had quit my VS Code, but here we are. So you have the transformers folder, and then inside that transformer models, you have a models subfolder, and then a bird subfolder, and then the modeling file is here. And since we've organized the code that way to avoid having all the files directly in the transformers folder, because as I said, we have like 60 different architectures, so that would be a lot of files. They are organized like this. And when you're trying to import, when you say from ... it's to go back inside that structure. So from import blah 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 would be in the bird folder, ... is in the models folder, and then the ... gets back to the transformers folder. So it's just a way to come back to the root of the directory. I didn't see any other questions, but don't hesitate to ask at any time in the chat your questions, and I'll answer as best as I can. And as I expected, my webcam is not showing anymore, and I have no idea why, because I just showed the video and now it's not working. Let me just write something. Here we are. Sorry about that. I had to just shut it down and restart it. So we're good to continue behind our exploration behind the pipeline function. And so we'll just take a little bit at the code that we just saw in the video. I'm not going to show it from the section side, but remember that in most sections, in all the sections that have code, you have an open in collab button at the top like this, which I opened a little bit earlier, just to execute the first cell, which is installing everything and can take a bit of time. And then the second cell, which is download the model, I executed it already so that we have the result instantaneously here. And we are ready to look at the rest of the notebook. So like in the video, let me move myself on the other side of the screen because the code is mostly on the left. So like in the video, we'll look exactly at the code that is executed when we try to use the sentiment analysis pipeline on two sentences like that, and see how we get to the results on those labels. So as we've seen in the video, the first step of the preprocessing is done by a tokenizer. So we'll look into the tokenizers in detail a little bit further ahead, but for now, you just need to know that the tokenizer takes the input text, so those two sentences. I've been waiting for the Hugging Face course my whole life, and I hate it so much. It's going to take those two sentences and convert them into numbers, because the model doesn't understand text, it understands numbers. So basically behind the scenes, it's going to split that text into small chunks that we call token, and so we'll tokenizer, and then associate each of those tokens to a unique ID, which is the numbers that we're going to see. To load the tokenizer, we need to know the identifier of the tokenizer. So here, this is the identifier of the model that is used by the sentiment analysis pipeline by default. And then we just call autotokenizer.fromPretrained, and it's gonna download if the files are already downloaded because I executed this first, but if it's the first time you're executing this, it's going to download the files of the tokenizer, and in particular the vocabulary, which contains the mapping token to unique ID, and instantiate it. And once you have that object available, you can feed it your input directly, like this, so raw input inside the tokenizer. And we'll exactly explain what those padding and truncation mean a little bit further ahead. And we tell it to return tensors. And since we are using PyTorch here, we tell it to return PyTorch tensor with this PT. You can also say TF for TensorFlow tensors, NP for NumPy arrays, or flags for flags, which is, I guess for flags, it's also NumPy arrays. And if we execute it, we can see that we get an output, which is a dictionary with input IDs and attention mask. We'll explain what the attention mask means a little bit further ahead in the course, in this last session, sorry. And the input IDs are the unique numbers I was talking about. So it's converted that text into small chunks of that are called tokens, and each of those tokens have been associated to a unique number. And once we have that, we can use the model on this input. Just if we want to have a look back. Why are you annoying me? If we want to have a look back at how those IDs correspond to the text that we had at the beginning, we can use the decode method of our tokenizer. So if I type tokenizer.decode, and then I'm going to take my inputs, grab the key input IDs. Oh, tick tick. Like this. So this is a tensor, so I'm going to convert it to a list and take this is a list of lists because I have the two sentences in my tensor, sorry. So I'm just taking the first one, for instance, and if I execute that, I can see my original text, which has been a bit preprocessed. There is no capital anymore for the I, for instance. And we can also see that the tokenizer added something at the beginning and something at the end. This is perfectly logical, as the tokenizer is adding those tokens because the model expects them. So I'm just going to pause here for questions before I go into the model part of the code. What does auto in auto tokenizer mean? And what type of tokenizer is used? So the auto for auto tokenizer in the auto tokenizer class means that you can load any tokenizer corresponding to any architecture using that API. So for instance, here our model is a Distilbert model. So the tokenizer is going to be a Distilbert tokenizer. You can double check that by just adding a console. If I type tokenizer and print the output, it's going to tell me it's a pretend tokenizer fast, which is not super useful. That's the representation is not super useful, but the type should be a Distilbert tokenizer fast. And if I had used a BERT checkpoint, I would have a BERT tokenizer fast. If I had used, I don't know, a BART checkpoint, I would have a BART tokenizer fast, etc., etc. So the auto in auto tokenizer means that that class is going to pick the right subclass of tokenizer, so when corresponding to the model used by your checkpoint, automatically. So your code here, tokenizer equals auto tokenizer.from pretrained checkpoint, is going to work for any checkpoint on the model hub. Whatever the class of your model, as long as it's a class of model that's been implemented in transformers, it's going to work on it. Whereas if you were using here Distilbert tokenizer, you would have to change the class used if you change the type of checkpoint. For instance, if you use a BERT model, you would have to change it to BERT tokenizer. If you were using a GPT-2 checkpoint, you would need to change it to GPT-2 tokenizer, etc., etc. The second question was, will IAM be broken into I and AM? And the answer to that is yes. We'll see a little bit. I'm just going to pause and answer more completely a little bit later when we see exactly the different type of tokenizers. And what is the difference between a fast tokenizer and a standard tokenizer? Very good question. So we usually have for each model two tokenizers, one that is called slow or standard, and the other that is called fast. The fast tokenizer is backed by the Hugging Face tokenizers library, which is not written in Python, but in Rust, and which in turn, because you may have known that Python is a slow language, and so if you do the whole tokenization in pure Python, it can be a bit slow when you have lots of text. Whereas the tokenizer fast backed by Rust is going to be extremely fast. So the main difference, that's the main difference between the two of them. If you're just processing one text, you won't see any difference. But if you're processing 10,000 of text at the same time, the tokenizer fast is going to be much faster than the Python tokenizer. And that's also a question we have for the moment. So I'm going to continue and look at the model. So the same way we have an auto tokenizer API, we have an auto model API. And again, the auto in auto model API means that this class is going to pick the right subclass, BERT model, GPT-2 model, distill BERT model, etc., depending on the checkpoint that it receives. So here, since it's a distill BERT checkpoint, it's going to output a distill BERT model. I can just show you here by tapping model, and it should have a nice wrap. We can see here distill BERT model. I'm gonna remove that cell because it's a bit annoying. Thank you for not so that model is coming with, again, we didn't download any file here because when we executed the pipeline instruction at the very beginning, we downloaded everything we needed. So the model is already cached. That's why we don't see any download here. And we get a warning, which I'm going to explain just after this cell, which is because this auto model class is going to give us the base pre-trained model. And this base pre-trained model doesn't output classification of our sentence between positive and negative. It outputs the hidden state of the pre-trained model, which is of dimension 768. So that's why here we have a warning, because that model, auto model, is missing a classification head. And as the warning was saying, some weights of the checkpoint were not used when initializing the model, specifically classifier bias, classifier weight, etc., which are all the weights of the classifier head. So auto model is something that can be useful if you just want the tensor of hidden features outputted by your pre-trained model. But here we want to classify our sentences between positive and negative, so we need a model with a classification head. And that's given to us by the auto model for sequence classification class. And this one, when I execute the cell, is not going to output any warning because all the weights are going to be used and there is not going to be anything problematic when loading the checkpoint. And if we give our input to that model and look at the shape, we can see that it's going to be a tensor of size 2 by 2. One little comment about the output is that the output of transformer models, so that was the thing that were imported at the beginning of our modeling file, if you remember, like we had a lot of import from the .model outputs module. So those outputs are a bit of an hybrid between a name tuple and a dictionary. So you can access everything either by doing dot like this, so outputs dot logit. You can also access things by asking with a key. So outputs, and then we ask for the logit key, like it would if like a dictionary, which works as well. And if we just ask for the base representation, we can see it's a sequence classifier output, which contain logit and this tensor. So here it contains only one thing, but most of the transformer model can return lots of things as outputs. For instance, if I added labels here, it would return a loss. We could also ask the model to return all the hidden states or all the attentions results, and in which case our output is becoming a bit crowded, which is why it's organized as this special class that behaves like a dict and like a name tuple. So those logits, because those are the names of what we get, are numbers which appear a bit random. They don't really look like probabilities, and we will need to do one last step of post-processing, as we saw in the video, to convert them into probabilities. That is, apply the softmax. And if we just import from Torch the softmax function and apply it, we can see that now we get the exact same score that we had at the beginning. So for instance, for the second sentence, like we have that 0.99, so 99.95%. And if we look back at the result of the pipeline, we can see that we had 99.945 here. So the exact same scores. And to know which one was the negative and which one was the positive label, the pipeline is using that field from the model configuration. So for each model, the configuration file associated to it is accessible via the config attribute, and the ID to label field contains the correspondence between integers and labels. So let's see if we have any questions. First question is there any reason to use a standard Python tokenizer? I work at a Tokening phase, so I'm a little bit biased and I'm going to say no. You have to, using the fast tokenizer is always going to be better. So it's going to be, even if you don't have many text, it's going to be at the same speed at the very minimum, or maybe faster than the Python tokenizer, standard Python tokenizer, but also it has many more features. So we'll look at them in the second part of the course mainly, but it has features that have been designed specifically for tasks like token classification or question answering that allow you to know, for instance, from which word a token comes from, or to exactly which span of text those tokens represent in the original text, which is features that are a little bit, not a little bit, way harder to get with the slow tokenizer. Another question is, are there any similar tutorials or resources for sentiment analysis for multi-labeled data or regression tasks for sequences? Not right now, that's a very good question. So not right now, and we should definitely work on that. So the main thing you would have to change is the post-processing at the end. Instead of applying softmax, you would apply, for a regression, you wouldn't apply anything, I guess. And then for multi-label, so multiple possible labels for each of your sentence, you would apply probably a sigmoid to your result. And then last question is, the first two input IDs of the two lines are the same, but the words are not. Why is that? So we have to look back at the decoding because the two words are indeed the same. So the sentence here begins with 101 and 101, which is the idea of that CLS token. So that's why you have the first two input IDs that are the same. And then the 1045 correspond to the I, because the two sentences begin with I, and then it starts being different because you have the or 8 for the two sentences. And another question, would it be possible to do a video explaining the code structure of the library and the ID behind it? So that's to maybe make it easier to contribute. Very, very good question, and it's actually scheduled for the last part of the course. In the part 3 of the course, we have a chapter that's going to be dedicated to how to contribute to the Hugging Face libraries, in particular the Transformers library. And then we'll have videos explaining the code structure of all the libraries of the Hugging Face ecosystem. Again, don't hesitate to ask any questions. I'm going to pause regularly to answer them. So that's pretty much everything that was behind the pipeline, and we've seen it in detail in the code. So now let's have a look at the main object inside the pipeline, which is the model. So again, we have a short video that I'm going to show from my computer, and then we'll look at the code in detail, and if you have questions, I can answer them and live code with you. Let me just grab the video. Which of course I can't find easily, otherwise that would be too easy. Why did it disappear? I'm almost there, I promise. I just moved it recently. And how to instantiate a transformers model. In this video, we'll look at how we can create and use a model from the transformers library. As we have seen before, the AutoModel class allows you to instantiate a pre-trained model from any checkpoint on the Hugging Face hub. It will pick the right model class from the library to instantiate the proper architecture and load the weights of the pre-trained model inside. As we can see, when given a BERT checkpoint, we end up with a BERT model, and similarly for GPT-2 or BART. Behind the scenes, this API can take the name of a checkpoint on the hub, in which case it will download and cache the configuration file as well as the model weights file. You can also specify the path to a local folder that contains a valid configuration file and a model weights file. To instantiate the pre-trained model, the AutoModel API will first open the configuration file to look at the configuration class that should be used. The configuration class depends on the type of the model, BERT, GPT-2, or BART, for instance. Once it has the proper configuration class, it can instantiate that configuration, which is a blueprint to know how to create the model. It also uses this configuration class to find the proper model class, which is then combined with the loaded configuration to load the model. This model is not yet a pre-trained model, as it has just been initialized with random weights. The last step is to load the weights from the model file inside this model. To easily load the configuration of a model from any checkpoint or a folder containing the configuration file, we can use the AutoConfig class. Like the AutoModel class, it will pick the right configuration class from the library. We can also use a specific class corresponding to a checkpoint, but we'll need to change the code each time we want to try a different model architecture. As we said before, the configuration of a model is a blueprint that contains all the information necessary to create the model architecture. For instance, the BERT model associated with the BERT-based case checkpoint has 12 layers, a hidden size of 768, and a vocabulary size of 28,996. Once we have the configuration, we can create a model that has the same architecture as our checkpoint, but is randomly initialized. We can then train it from scratch like any PyTorch model. We can also change any part of the configuration by using keyword arguments. The second snippet of code instantiates a randomly initialized BERT model with 10 layers instead of 12. Saving a model once it's trained or fine-tuned is very easy. We just have to use the savePretrain method. Here, the model will be saved in a folder named myBERTModel inside the current working directory. Such a model can then be reloaded using the fromPretrain method. To learn how to easily upload this model to the hub, check out the Push to Hub video. Okay, so let's see if we have any questions. Not just yet. Don't hesitate to ask any question in the chat and I'll answer them regularly. And for this, let's open the Colab and look a little bit at the code behind the AutoModel API. And in particular, we'll see, for instance, I told you a little bit earlier that our model could return more than just the logits, and it could return, for instance, all the hidden states or things like that, and we'll see how to do that just here. Yes. So, if you had any questions, now would be an ideal time because I didn't execute this notebook in advance, so we need to wait for it to install everything. Okay, that didn't take so long. So, to create a random model that looks exactly like the BERT model, we can just instantiate the default configuration and use that configuration inside the model. Like we saw in the video, the config contains lots of fields that are related to what's happening inside the model. So for instance, we have the hidden size configured, We have the number of words that our model can take in. We have the vocabulary size, the model type, which is bird, the activation it's used, which is kilu, etc., etc. So that model, using just a random, using just the config, is going to be randomly initialized, and there is nothing to download there. If we want to use a pre-trained model, we have to use the from pre-trained method, which is going to download the exact config, and then the model weights. And as we saw in the video, it's going to use the config to first instantiate a randomly initialized model, and then load the weights from that checkpoint inside the model we have. And if we want to change anything in a model, more specifically in its configuration, we can say it in several places. So for instance, we can start with a config that is exactly like bird. So autoconfig.from pre-trained bird pascased, which is going to download, and it's already downloaded from here. Oh, what do you mean autoconfig is not defined? Oh yeah, I've only used bird config, so let's continue with that. So bird config.from pre-trained, which is going to reuse the config that was downloaded here. So this is the configuration of the bird model. And if we want to change anything inside it, we saw in the video, for instance, how to change the number of hidden layers. But let's say that I want to change the fact that I want my model to return all the hidden states, which I would say with output hidden states equal true. So I can do this in the config and then instantiate my model with model equal bird model config. I can also directly change this when I do bird model.from pre-trained here. So since if I were to change here the number of hidden layers, it wouldn't work anymore. The command would fail because I would then try to load a checkpoint that has been defined with 12 layers inside the model with 10 layers. So PyTorch would complain. I mean, it would probably work, but I would have a warning with like the weights not being used, and the model would probably not get super useful results. But for something like output hidden states, which doesn't really change the way the model was pre-trained, this is going to work super nicely. And if I try to take inputs, so let's define some random input and then pass it to a tokenizer. So I'll have to use a bird tokenizer and then instantiate it with the from pre-trained method. Should have yes, it's finding it here. Should have executed the cell already. So if I'm creating a tokenizer like this, and then applying it to my inputs, return a tensor. I don't need to put the padding and truncation that we saw before because there is only one sentence. We'll see why a little bit earlier. So once I have done that, I can look at my outputs. And it should have now 2 keys, still 1 key. Yeah. with a little bit more, because the BERT model has a polar output, on top of the logits, and it's not logits anymore. Sorry, it's last hidden states, because this is not the classification model; it's a base model. I used a BERT model, which is the same as using auto model, not a BERT model for sequence classification. So I get a last hidden state instead of logit key. The polar output is specific to BERT, so it always has that. And then I can see I have a last key with hidden states and a list of all the tensors which correspond to all the hidden states of my model. So this is how you change the configuration of your model on the fly, either inside when you create the config, if you are trying to initialize a randomly initialized model, or to the from pre-trained method if you are trying to use a pre-trained model. In particular, if you're using a classification model, for instance, a sequence classification model, you can specify the most important argument is going to be num labels, because when you add your classification head, you want to control how many outputs that classification head has. So you would do that with the num labels argument. So that model, and then once you finish training or fine-tuning your model, you can use save pretrain to save it on the floor on your hard drive, and you can use push to hub, which we just released today actually. So on your model to directly upload your model on the Hugging Face hub, so that anyone in the world can use it. I don't see any questions. Again, don't hesitate to ask any questions. I'm going to answer them regularly. And so this is all we have to, this is all there was in the section for models. And then let's look at the tokenizer, which is responsible for pre-processing the input. I'm going to move myself, oh, not the screen, come back. I'm going to move myself back on the left, because we look at this section here and not at the code inside the collab. So tokenizer. Oh yeah, let's look at the video with tokenizers overview first, and then I'll comment everything that's happening in this section. So tokenizer introduction video.
In the next few videos, we'll take a look at the tokenizers. In natural language processing, most of the data that we handle consists of raw text. However, machine learning models cannot read or understand text in its raw form. They can only work with numbers. So the tokenizer's objective will be to translate the text into numbers. There are several possible approaches to this conversion, and the objective is to find the most meaningful representation. We'll take a look at 3 distinct tokenization algorithms. We compare them one-to-one, so we recommend you take a look at the videos in the following order. First, word-based, followed by character-based, and finally, subword-based.
So we won't look at the video, actually we're going to look directly at the text inside the course, and I'll comment because we won't have time to watch all those videos in the slot we have. So word-based tokenizers, so you can look at the video in your free time, but we're going to explain it a little bit more in depth than what I'm about to do. But the word-based tokenizer, it's just going to split your sentence by word. So the easiest way to do that is to take all the spaces and then split your text on those spaces. More advanced would be to include some rules to split and punctuation. So for instance, the exclamation mark separated from tokenization, or here let's split it between let and apostrophe s. So we can see this on this example with Jim Henson was a puppeteer, which is separated into 5 words here. So the word tokenizers were used a lot before transformers mostly. The advantage is that you split naturally your text onto the spaces and punctuation. The disadvantage is that you end up with pretty large vocabularies because there are lots of different words in English, and every time someone makes a typo in some word, you end up with a new with another new word in your vocabulary. So each word gets assigned an ID, starting from 0 going up to the size of the vocabulary. And then, since we can't guarantee that the user is never going to make a typo or anything, there is a special rule. If we encounter a token that doesn't exist in the vocabulary, it's usually replaced by something called the unknown token, which is usually something that looks like that, unc between brackets. So this is one of the other drawbacks of the word-based tokenizer. So the first one is that they have very large vocabularies. The second one is that they need to learn that the word dog and the word dogs are very similar. They won't know that from scratch because when the model is initialized randomly, it's going to have a set of embedding for that word dogs and another one for that word dogs. And it's going to need to learn by seeing lots and lots of data that those two words look a bit alike. And the last disadvantage is that unc token. So every word that's a typo is going to end up like this, and the model can't really learn any representation of that. It's going to it's as if you had just deleted the word in the sentence. So another way is to just split your text on all characters. So which is what character-based tokenizers do. In this case, your vocabulary is not going to be very large because there are 256 ASCII characters, for instance, a little bit more if you take the whole Unicode thing, but you're not going to end up with models that have a vocabulary size of, I don't know, 300,000 or something like that. So this is better for the vocabulary size. You probably won't get an unknown token because you all see all the different characters possible. But the drawback is that now the representation is based on character. So the model has to learn that, for instance, the letter E does not mean the same thing when it's between an L and a T, where compared to the letter E here with the K and the N inside the word tokenization. So the representation of each letter is less meaningful. That's what I'm trying to say. And compared to what we had with words. The other drawback is that we end up with very long sentences. For instance, for let's do tokenization, if we look back to our word-based tokenization, it was split into 5 words. With the tokenization, with the character-based tokenization, it splits in much more. Can't count here, but it's in between 15 and 20, I'd say. So we end up with longer sentences, and our transformer models are usually constrained by a maximum length. So, for instance, the BERT model can only can only treat 512 tokens at a time. So, using a character-based tokenization algorithm would make the maximum sentence you can feed the model pretty short. So that's why transformer models usually use a compromise between word and character-based tokenization, which is subword tokenization. So subword tokenization, as the name indicates, is going to split your text into subwords. So it's still split between words, but some words are cut into. For instance, here you've got let's, do, and then token and ization are separated into. Notice that you get this small end with like the, I never know to say that in English, but that special thing between an inferior and superior sign with /w, which means that it's the end of a word. So token doesn't have it because that's because we want the model to be able to differentiate token as a single word and token followed by something else like tokenization. So the ization has the suffix that says here it's in the other word, but token does not. And so that depends on the convention used by the tokenizer. Some tokenizers have a thing at the beginning of words, some tokenizers have a thing at the end of words. And so this approach allows you to have a vocabulary that's not going to be too huge, and the tokens still have some meaningful semantic, some semantic meaning that's more meaningful than just characters. And the last thing is that for words-based tokenizers, for instance, dog and dogs were two separate words. Here, dogs would probably be split into dog and an S, the same way tokenization is split between token and ization. So it can learn that they have the same prefix, and then the suffix ization is going to be used in other words like modernization, and the model can then make sense of those suffixes and learn that they are always kind of the same. And so in the next part of the course, we'll look at into detail the different, because there are three different subword tokenization algorithms that are byte level, word piece, and sentence piece. We'll explain exactly the difference between them in the next part of the course. So let's see if we have any questions before we look at how the tokenizer work in practice. Yes, I'm just going to put myself here properly. Tokenizer breaks a sentence into tokens, but no lemmatizations or stemming is performed before learning. It's... Let me double check. I would say no, but you should ask the question in the forum where people that are more competent than me can answer you, because I'm not completely sure. Could you provide intuition into word piece used in BERT and sentence piece type tokenizers? I could, but it's going to take a bit of time. So again, I'm going to redirect you on the forum where I can take the time to properly answer you. And there is also, maybe Lewis can share it here, there is a tokenizer summary in the Transformers documentation that explains the difference between word piece and sentence piece, which is using Unigram behind the scene, and the key differences between the two. Does the W/W tag add any information in the subword tokenization? So yes, as I said, it's what allows the model to know the difference between a single word, between token used as a single word or token inside a word like tokenization or tokenizer. And then let's see how the tokenizer work in practice. So we have seen how to load the tokenizer using the from pre-train method and what it returns. And we'll now quickly look at the video on the tokenization pipeline, which is going to explain what happens when we feed the tokenizer a sequence like that and how it returns those numbers. Let me just grab it from my computer and then I'll continue answering questions. The tokenizer pipeline. In this video, we'll look at how a tokenizer converts raw text to numbers that a transformer model can make sense of, like when we execute this code. Here is a quick overview of what happens inside the tokenizer object. First, the text is split into tokens, which are words, parts of words, or punctuation symbols. Then the tokenizer adds potential special tokens and converts each token to their unique respective ID as defined by the tokenizer's vocabulary. As we'll see, it doesn't quite happen in this order, but viewing it like this is better for understandings. The first step is to split our input text into tokens. We use the tokenize method for this. To do that, the tokenizer may first perform some operations, like lowercasing all words, then follow a set of rules to split the result into small chunks of text. Most of the transformer models use a subword tokenization algorithm, which means that one given word can be split in several tokens, like tokenize here. Look at the tokenization algorithms video linked below for more information. The # prefix we see in front of eyes is a convention used by BERT to indicate this token is not the beginning of a word. Other tokenizers may use different convention, however. For instance, Albert tokenizers will add a long underscore in front of all the tokens that had a space before them. which is a convention shared by all sentence-based tokenizers. The second step of the tokenization pipeline is to map those tokens to their respective IDs, as defined by the vocabulary of the tokenizer. This is why we need to download a file when we instantiate a tokenizer with the from pretrained method. We have to make sure we use the same mapping as when the model was pretrained. To do this, we use the convert tokens to IDs method. You may have noticed that we don't have the exact same results as in our first slide. Or not, as this looks like a list of random numbers anyway, in which case allow me to refresh your memory. We had a number at the beginning and a number at the end that are missing. Those are the special tokens. The special tokens are added by the prepare for model method, which knows the indices of those tokens in the vocabulary and just adds the proper numbers in the input IDs list. You can look at the special tokens and more generally at how the tokenizer has changed your text by using the decode method and the output of the tokenizer object. As for the prefix, for beginning of words, part of words, those special tokens vary depending on which tokenizer you're using. The BERT tokenizer uses CLS and SEP, but the Roberta tokenizer uses HTML-like anchors, S and /S. Now that you know how the tokenizer works, you can forget all those intermediate methods, and only remember that you just have to call it on your input texts. The output of the tokenizer don't just contain the input IDs, however. To learn what the attention mask is, check out the batch input together video. To learn about token type IDs, look at the process pairs of sentences video. So we have one question that's linked to what we were saying just before the video. Are token /w and token going to have separate representation IDs? And yes, they are going to have separate representation IDs because they are not the same token, which is the whole meaning of that /w token. Not token, sorry, suffix. So, tokenizers, the tokenization pipeline. I'm not going to live code those intermediate methods because you shouldn't really learn them. We're just showing them to show you the steps inside the pipeline. The main thing to remember is that you just have to call your tokenizer on your input like this, because this is the main API that's the most useful. And now we'll look at what the attention mask is and what padding and truncation means, the arguments that we had at the very beginning, so that we've fully explained what's happening inside all the tokenizer. Oh, another question. Is there a reason you would save a pre-trained tokenizer other than that to just have a local copy? Very good question. So yeah, there is no real reason to save your pre-trained tokenizer if you don't need to if you didn't make any change inside it, and you would always have a local copy because autotokenizer.from_pretrained is going to cache the files to avoid you downloading them again. So there is no reason to save it. The one exception is when you're creating a folder that you want to push to the model hub, in which case you should save your tokenizer inside that folder so that when you push to the hub, you push your model, the configuration, and the tokenizer that's used with it. And with all those three things, the Hugging Face website is going to be able to apply the inference API in your model, and you will be able to play with the widget online. Other than that, you won't really need to use the save pre-trained method on the tokenizer. It's mostly for the model that's going to be super useful. Or, and we'll see in part 2 of the course how to do that, if you're training a tokenizer from scratch because you're pre-training a model, for instance, in a new language, then you'll need to use the save pre-trained method to save the result of your tokenizer. So we're going to watch the last video for today's live session about batching inputs together, and then we'll look more closely at the code together. Let me just launch the collab first so that we don't have to wait after the video, and then we'll watch the video together. Come on. Shoof. Yes, I want to run it. And let me grab the video, batching inputs together. how to batch inputs together. In this video, we'll see how to batch input sequences together. In general, the sentences we want to pass through our model won't all have the same length. Here, we are using the model we saw in the sentiment analysis pipeline and want to classify two sentences. When tokenizing them and mapping each token to its corresponding input IDs, we get two lists of different length. Trying to create a tensor or an NumPy array from those two lists will result in an error, because all arrays and tensors should be rectangular. One way to overcome this limit is to make the second sentence the same length as the first by adding a special token as many times as necessary. Another way would be to truncate the first sequence to the length of the second, but we would then lose a lot of information that might be necessary to properly classify the sentence. In general, we only truncate sentences when they are longer than the maximum length the model can handle. The value used to pad the second sentence should not be picked randomly. The model has been pre-trained with a certain padding ID, which you can find in tokenizer.padTokenID. Now that we have padded our sentences, we can make a batch with them. If we pass the two sentences to the model separately and batch together, however, we notice that we don't get the same results for the sentence that is padded. Here, the second one. Is that a bug in the transformers library? No. If you remember that transformers model make heavy use of attention layers, this should not come as a total surprise. When computing the contextual representation of each token, the attention layers look at all the other words in the sentence. If you have just the sentence or the sentence with several padding tokens added, it's logical we don't get the same values. To get the same results with or without padding, we need to indicate to the attention layers that we should ignore those padding tokens. This is done by creating an attention mask, a tensor with the same shape as the input IDs, with zeros and ones. Ones indicate the tokens the attention layers should consider in the context, and zeros the tokens we should ignore. Now, passing this attention mask along with the input ID will give us the same results as when we send the two sentences individually to the model. This is all done behind the scenes by the tokenizer when you apply it to several sentences with the flag padding equal true. It will apply the padding with the proper value to the smaller sentences and create the appropriate attention mask. So let's look at the same thing in Colab. Unless there are any questions. No, I don't see any new questions. Don't hesitate to ask your questions in the chat again. And let's look at the same code that we had to look again at what the padding and attention mask are exactly. So as we saw in the video, if we try to apply our model directly. Oh no, it's not the exact same thing as in the video. If we try to apply our model directly on just one sentence that we tokenized and converted to IDs like that, using the same code as in the previous video, it's going to fail because the model wants batches of input. So it wants, it the tokenizer, even if you have just one sentence, is adding one dimension. You can see like there are two pairs of brackets surrounding that. So here this is a tensor of shape 1 by, I guess, 16. And so if you want to pass just one sentence that you processed manually to a model, you have to add one dimension, for instance, by adding a pair of brackets here. This is for a separate example. So now, looking at two sentences together, so if we have two lists, so let's say we have those IDs and those IDs, and we want to make a pair of sentences, we can create a list of lists like that, but we can't create an array with the two of them because they don't have the same shape. So we need to add a padding index. So we could either add it at the end or at the beginning. Most of the transformers model expect the padding to be applied on the right, with the exception of XLNet, which expects it at the beginning. But the tokenizer should be responsible to apply the padding because the tokenizer knows what the model wants and it's going to apply it on the right side. So once you have those batch IDs, you can create create tensors from them and then pass them through the model. And if we look, like we've just done in the video, at the outputs, if we pass the sentences separately, so we still have to add a pair of brackets if we want the model to be applied on them, because the model expects a batch. So the batch can have just one thing inside it, but it needs to be something that has 2 dimensions. So if we pass sequence 1 and sequence 2, we get those 2 results. And if we pass the batch with the 2 sentences, we get the same result for the first sentence, but a different result for the second sentence. We can see that those 2 are different here, which is because the second sentence with the padding token, if we don't do anything special, the model is not going to compute the same results. It's not going to properly ignore the padding token. So that's, as we saw in the video, is because of the attention layers. The attention layers are at the core of the transformers model. And they are we explained that at length during chapter 1. There are layers that not compute a representation not just of one word, but one word within its context, because transformer models were designed for translation at the very beginning. And if we want to translate a word, we don't just need to pay attention to that word, but to all the words around it. For instance, to know which gender the word had, if it's a singular or plural noun, things like that. And so if we don't if we don't tell the attention layer that this is not a real token, it's just a fake token we needed to add to have a rectangle and make a batch, the attention layer is going to pay attention to that token and compute a contextual representation that has that token into account. So to tell the attention layer, no, that's not a real token, don't pay attention to it, we have to create what is called an attention mask. So here we put ones where we want the attention layer to pay attention, and zeros where we want the attention layer to ignore. So it has the same shape as the batch IDs that we are using, and the 0 is put where we have the tokenizer.paddTokenID. And if we do that and pass those through the model, now we see that we get the same output. So here, the first sentence is still the same because there was no padding, but this output here is the same as this output here, which was the output of the model with the second sentence. So this is what's done by the tokenizer. If you remember, when we were passing our 2 sentences, it was returning something with 2 keys. One was the input IDs, which correspond to this thing here, and the other one was the attention mask, which corresponds to this thing here. The truncation argument, so when we passed the 2 sentences to our tokenizer at the very beginning, we said padding equal true and truncation equal true. So truncation equal true is going to truncate very, very long sentences, because for instance, BERT model, for instance, can only handle sequences that have a length of 512 maximum. So if we have a sequence that's longer than that, the model is going to fail, and we need to truncate it. You shouldn't truncate your inputs for any other reason than making them shorter than the maximum length the model can handle. Otherwise, because when you truncate, you remove information. So for padding, we are adding something, and we can tell the attention layer to ignore it. So at the end, we get the exact same results with or without padding, but with truncation, you're ignoring information that you just can't recover. So you will never be able to get the same results with or without truncation. But sadly, it's needed because transformers have a maximum length. So if you have very long inputs that are greater than that maximum length, you need to truncate them. And if we go back looking at the course, in the putting it all together section, we have the various padding and truncation strategy. So here, so if we go back with the 2 sentences we were using at the very beginning of this last session and pass them, we can pass them to the tokenizer, which is going to then output list of lists, but we won't be able to batch them together without applying padding. So there are various strategies to apply padding. When we do padding equal true, it's the same as doing padding equal longest, which is going to pad the sequences up to the maximum length inside the samples that you're passing. So here, we have 2 sequences with padding equal longest. It's going to pad the second sentence here to the length of the longer sentence. If we go back to the notebook behind pipeline, we can see that here with all those zeros being added so that the second sentence inside the batch is the exact same length as the first. You can also say padding equal max length. Max length refers to the model max length. So for instance, it's 512 for BERT or DistilBERT. So this is going to pad every sentence to 512, the maximum length of the model. That option should not be considered when you have short sentences, for instance. In general, it's better to pad to the longest thing you have, unless you need to use fixed shaped for some reason. For instance, TPUs like fixed shapes better, in which case you would use the max length option, and which is a bit inefficient. But for instance, with the TPU accelerator, it's the only way to get some real speed, because they need all the inputs to have the exact same shape. And you can also specify a max length that you want. So for instance, if you know that in your dataset all your sentences are shorter than 128, you could say padding equal max length equal 128. And so you should also use truncation, as we said, because you need to truncate when your inputs when they are longer than the maximum length a model can handle. You can also specify the maximum length to which you want to truncate your inputs. So that's it for padding and truncation. Do you have any questions? No questions. More links shared by Lewis. So the last thing is, as we saw before, you can tell your tokenizer to return PyTorch tensor, TensorFlow tensor, or NumPy arrays. And as we saw in one of the videos, the tokenizer pipeline video specifically, the tokenizer adds the special token at the beginning and at the end of our sentence. So it depends exactly on which model you're using, but the tokenizer will know what special tokens the model expects, and will put them at the beginning and at the end of your sentences. And so to conclude this chapter, here is the whole code. It's just missing the post-processing, but here is the whole code that was executed behind the scene by the pipeline. So you import auto tokenizer and auto model for sequence classification. The auto meaning that you can use any checkpoint from the hub. It's going to pick the right architecture for you. The checkpoint that was used by the pipeline is this one. You can use any other checkpoint on the model hub that correspond to a sentiment analysis task. We can load the tokenizer with the from pretrain method. We can load our model with the from pretrain method. And if we have two sentences, we can tokenize them together with padding equal true, truncation equal true, return tensors equal PyTorch, if we're using PyTorch, TensorFlow if using TensorFlow, and then we pass those tokens to the model. And to get the post-process results, it's just missing the softmax here to have the exact same result as the pipeline. One last question. I'm confused between padding equal longest and dynamic padding. Is it similar? Yes, it's very, very similar. We'll look at dynamic padding in the next chapter when doing training. But for those who don't know what it is, dynamic padding is when you go through your training data and build batches. Dynamic padding means each time you have to build a batch, you pad your sentences to the maximum length inside the batch. And so that's what padding equal longest will do. If you pass your sentences, a small batch of sentences is going to create a batch with, for instance, 8 sentences, and the second dimension is going to be the maximum length inside that batch. Whereas padding equal max length is going to pad everything to a fixed max length, either the maximum length the model can handle or the maximum length you passed along to the tokenizer. And so that's it for the basic use of models and tokenizers. Thank you for following the live stream. So now that we have seen that chapter together, you should be able to complete the questionnaire at the end. And then before going to chapter 3, it's useful if you try to run again the pipeline collab that we saw together and the batching input together collab that we looked at together, and try to understand what every cell is doing, and maybe even try to redo it yourself. And then try to think of a problem you want to work on, a classification with a text classification problem you want to work on, and try to use a base model and a tokenizer on that problem to be able to get outputs from some inputs. And we'll see in the next chapter of to actually fine-tune a model on your given problem. And in chapter 4, we'll see how to upload the result to the Model Hub so that you can then share that model with the rest of the community and use the widgets of the Inference API online to have demos of your model. Let me look at the questions before we end this live stream. Oh, following up from the previous question, with padding equal longest, we don't need to use data collector with padding. That's not entirely true, and we'll see exactly why in the next chapter. We need to be in the dynamic of training a model. If you are playing padding equal longest while doing tokenization on your whole dataset, it's going to pad to the longest element in your dataset. So that's not really the same thing as doing dynamic padding. But yeah, we'll dive into that in the next chapter. Otherwise, thank you all for following this live stream. And next week on chapter 3, there are 4 different live streams because the chapter 3 is very different for PyTorch and TensorFlow since it's about training and fine-tuning. Up until now, the code had some little differences, and you can see that you have a switch here for the course if you want to switch between PyTorch and TensorFlow. If you want to look at exactly those differences, but for next chapter, it's going to be very different. So you have live sessions specifically for PyTorch and live sections specifically for TensorFlow. Be sure to check on the forums which one you want to attend to and mark it into your calendar. And yeah, let's wrap this up. Thanks a lot for coming. Bye-bye.